In part C, we are asked to send a modulated signal and do some measurements on this signal at the receiver side. To do this, starting with the transmitter, we pick the frequency again to be 460 megahertz. And for amplitude, we also pick minus 30 dPm. Now the further step that we have to make is the modulation. With this option here, we choose arbitrary custom modulation, and we make sure that digital modulation is on. Then we move to single carrier setup. Now for modulation type, we are asked to pick QPSK, so I will choose it here. So I'll return back. For filtering, we are asked to choose root raised cosine, which is selected by default, and its roll-off factor is 0.3. Now there are other options which are the oversampling ratio and span of the filter, which are not provided here in this built-in software. So I will return back. That's it for the filter. The last thing is the sample rate, which is 20 kilo sample per second. So the transmission parameters are ready, so we can start transmitting by turn on the modulation and the RF transmission. Now at the receiver side, again, we pick 460 megahertz and the span to be 1 megahertz. We can auto scale, and we can see here our signal. We can do averaging as we saw earlier. Let's pick like 100 snapshots and repeat. Start again, and we see here we have more spectrum occupation because the signal is modulated. We have pulse shaving. It's not a DC envelope. So let me turn off the averaging. Now to do further measurements, we have to change the measurement type. So we go to measurement setup, and for measurement type we pick digital demodulation. Now before going through the detail of these traces here, we need to also change the demodulation properties and set the parameters the same as we picked them for at the transmitting side. So for modulation we have QPSK. For sample rate we have 20 kilohertz, and for filtering we have root raised cosine, but the alpha factor is 0.3. Now we close it. Now we see that the polar diagram is making more sense now. Now we will see 4 different measurements for now. So I will adjust the traces layout here to be a grid of 2 by 2. We will see the polar diagram, so I will not touch it here. And we will see the spectrum also, so we will leave it, but I will just auto scale it here. Now here let's see the constellation. So to see the constellation, we go to this drop down menu here, and we pick IQ measurement time, and here we double click and we choose constellation, and here we see the constellation. Now here let's see the eye diagram. So the same IQ measurement time, and here we pick either the eye diagram for the in quadrature or in phase or quadrature component, any one of them. So here is the eye diagram. We can adjust the reference level, reduce it since we have a low transmitting power. So we reduce the attenuation applied by the VSG, and as we see, the constellation diagram has less noise here because we increased the signal to noise ratio. Let's see what would be the effect if I increase the transmission rate. So let me just pick a marker and put it somewhere here at this edge. And now back at the transmitter side, let's change the sample rate. So I will turn off the modulation and RF transmission, and I will go back to modulation setup and single carrier. And here for sample rate, let's pick 35, for example, kilo samples per second, and start transmitting again. Now here we notice that the spectrum is more occupied because the sample rate is higher. but the diagrams here are more messy and make no sense. And the reason is, as we change the transmission rate parameter there, we have to change it here as well. So we go to demodulation properties and change it here to 35 kilohertz. So we have them back again as the case of 20 kilohertz. Now let's go back to the vector measurements, and let me close these two traces and auto scale the spectrum. Now to measure the signal to noise ratio, one way is as follows. We go to the transmitter and we stop the RF transmission. Then back to the VSA, we measure the signal, the noise power over the whole band. We do this by picking the band power tool and put it at the center. Then we move its boundaries to the edges of the selected band. And as we see here, the noise power over the spanned band is approximately minus 91 dBm. Now back to the transmitter, we transmit again, and here back to the VSA, we move the boundaries to the null to null bandwidth of the transmitted signal. To have a better view, as we know, we can do averaging as well. Let's do one-shot averaging for 500 snapshots. And here we have the null to null bandwidth, and the measured signal power is minus 54.2 dBm. Now let's also see the effect of the roll-off factor again. Once we have averaging, we can see clearly the occupied bandwidth. So let me put the marker somewhere here. And back to the transmitter side, let me turn off transmission, and in modulation I will change the roll-off factor to be, for example, 0.9, let's say, and start transmitting again. Now we see how the shape of the occupied bandwidth has changed. Now let's make some bandwidth measurements. Before starting these measurements, let me just make the averaging one shot by stopping this repeating option. So starting with the null to null bandwidth, we can use this tool, which is band power, and click here at the center. By default, these rulers will be at the center. We can move them to any location, which in our case here is the edges. So it will give me now the power within this band, which is minus 48.5 approximately dBm. Now for the occupied bandwidth is the band where we have 99% of the received power. So we can see it by clicking this option here, and it's shown here in this blue shaded region. For the 3 dB bandwidth, the 3 dB frequency is the frequency at which we have a drop by 3 dB of the peak value of the spectrum. So here at the peak we have a value. Let me just remove these two bands. We have here a minus 59 approximately dBm. So I expect the frequency at the 3 dB frequency to have an amplitude of minus 62 dBm. So I can slide it as we see here, and it's approximately at this point. To compare it with the occupied bandwidth, we can show it again here. Finally, we will receive some standard signals using the VSA. These signals are the Wi-Fi and Bluetooth signals. Both operate at the 2.4 GHz band. So I have an antenna operating at this band connected to the VSA, and here I have the center, the frequency as shown here. And now I have a mobile device connected to a Wi-Fi access point, and this device is close to the VSA. Now I will start a speed test, so some Wi-Fi signal will be, Wi-Fi packets will be received by both this device and the VSA. So let me start. So now here we see the the packets being received. To have a better view, we can use the spectrogram. And here we see the Wi-Fi frames. We can enlarge this trace. Now, as we said, Bluetooth also operate at the same band. So let me stop this speed test first. And I have a Bluetooth speaker close to the VSA and connected to the same mobile device. I will play some files so data will be transferred to that Bluetooth speaker. So let me start. Bluetooth uses frequency hopping. As we see, here are these hubs correspond to the Bluetooth packets.